in this video we're going to talk about how to do the calculations for your motion and graphical analysis lab. But what in the world are we supposed to be calculating anyway? Well, the answer lies in the Unit 1 folder, as usual, because we're in Unit 1, in one of these three documents right here. There's one PDF version of it, there's also a Word document, and there's a Google Docs version of it. All of those essentially open the same thing. I'll open the PDF so you can look at it. This is the handout for the lab, which you may have looked at before because after all we did the lab in class. This page right here, page 4, is where you find the things that you're supposed to calculate. Okay, so for example, it says constant velocity, gives you some hints here about how to calculate stuff, and then this is the table of things that you're supposed to calculate for each of the various runs. Positive acceleration has its own list, negative acceleration has its own list. This lab could be called the Newton was right lab, or maybe the calculus lab. Either way, the point of it is to show that the displacement, as measured by your position versus time graph for each run, is the same as the displacement as calculated for your velocity versus time graph. We are going to begin by looking at the constant velocity graphs, and specifically the position versus time graph, and show how we fill in each of these lines here. So here is some data that I processed, and this first graph is the, as we can see, the position versus time graph. This is what they should look like. More or less everybody's going to have the same kind of thing for their constant velocity graph. And right here where it says equation of line, literally all you really got to do is write down that equation. Sounds good. Okay, next line down. Average velocity. Well, to answer that question, you've got to remember something about calculus, which is that the average velocity over some time interval for a graph like this is the slope of that line. Let's say it another way, in more calculus words, the derivative of position is velocity. Given that this is a position graph, the derivative of it, or the slope, is the velocity. Looks like it's got a relatively constant slope, right, because it's a straight line. If I was wondering, gosh, how would I find the slope of that? Don't do anything extra. It's already right there. You already have the equation of the line provided to you by Google Sheets or Microsoft Excel or whatever you're using. Okay, fine. There's the average velocity. Okay, that took not that much effort so far. The next few ones are actually also going to be super easy. It says x naught. What is x naught? Well, that would be the initial position. That's that's this point. Gosh, what is that number? Don't try to read it off the graph. That's a mistake. Instead, you should go to your data table. So here I am back at the data table. Looks like that first data point, its value for the position is 0.18. Awesome. So I will write that down. 0.18 meters is my initial position. My final position, way the heck over here, again, I can look in my data table to get exactly the number, is 0.97. And now to get the displacement, that's change in position. That's going to be the difference between those two values. So subtract them and you get 0.79 meters. All right, well, now what? Well, now we're going to figure out everything from the velocity versus time column, such as the equation of the line, the acceleration, okay, all the rest of it. Coming over here, this particular constant velocity graph gives me, let's see, the equation line is 0.02x plus 0.53. Okay, all right. Acceleration is the derivative of velocity. Derivative is a slope. The slope of this, quote, line, it's pretty flat, but it's a line, is 0.02 meters per second squared. Super squared. Fine, those were straightforward. All right, this next one, getting the displacement, is definitely the most complicated bit. If you want to get the displacement for this graph, it's not the same thing where you just look at the first number, look at the last number, and subtract. Instead, you're going to have to do an integral. Well, what is an integral? An integral is the area under a curve, or really any kind of a graph. And so this right here that we have is basically a box, right? Area always goes all the way down to the axis, or all the way up to the axis, depending where you are. And it's Kind of hard to appreciate in this circumstance, but we have a rectangle with an extremely super skinny triangle above it. Maybe you could appreciate that better had I drawn a straighter line, but we'll just go with it, all right? So this area up here is a triangle, and down below we have a rectangle. All right, well, let's see. Area of a rectangle. That would be length times width. And triangle, you know, of course, is 1/2 base times. Now all we've got to do is figure out, all right, what are length and width and base and height for this rectangle and triangle here. Now, you might be immediately tempted to go look with the picture we've drawn here and say, oh, well, this is easy. The length of the rectangle is going to be like, I just like figure out what this value is down here, and that's going to be it. Careful. The length is actually going to be found by subtraction, right? You've got this point and that point. Those define where the edges of your rectangle are. So this length dimension here isn't just like, look up this number in your table, your data table. It's going to be, you got to look up this value and that value and subtract them. All right, let me find those. Looks like my last time value is at 2.3 seconds. And my first value is at 0.9 seconds. So that means that my length times width is going to be 2.3 minus 0.9. Okay, and then for the width is going to be, depending on which way the triangle part here is sloping, you're either going to pick this value, the initial velocity, or you're going to pick the final velocity. In my case, the lower end is the initial velocity here. So I will look up in my table, looks like it's 0.54. And so since this is here at 0.54, that's going to be how tall my rectangle is. So I'll put in 0.54. I'll worry about what that is in a minute. First, let's go ahead and figure out what we're going to plug in for 1/2 base times height. The base of the triangle is, well, it's this thing, right? Which is the same as what I just figured out down here, right? The base, or the rectangle and the triangle have the same base. So 1.4. And then the height of it is going to be based on whatever the final velocity is for that interval. I'll just go with the number from the table, 0.57. All right, now that 0.57 is not the height of my triangle. It's a skinny little triangle, right? The height actually is 0.03. That would be 0.57 minus 0.54. So 0.03. Right, got to subtract those two to come up with the height of the triangle. All right, now I'll get all that into a calculator and we'll come up with the total area. Now, sheets in Excel, remember, are both calculators. So here I've calculated the area of the triangle, the area of the rectangle, and add them all up, and it's 0.777. Wow, okay. All right, so that's the area. If you've forgotten what we were doing, the area was the displacement. So 0.777 meters is how far the cart traveled based on the velocity versus time graph that we've got. All right, now, if we think back to moments ago, we also came up with a number from our position versus time graph. That value was, not that, 0.79. So this one said the displacement was 0.79 meters, but we've got a slightly different value down here. That runs to like 0.78, but that's not the same number. All right, is that a problem? No, not really, actually. This is pretty darn good. Now, I can eyeball it and say those two are basically the same number, but you're going to actually go ahead and calculate something called a percent difference in order to show that those are the same number. Here's where you're going to find the formula for percent difference. All right, if I go back to my shared folder here, go up to Unit 0, and there's this document here called Laboratory, no, sorry, that's not it. Laboratory requirements. You definitely need to read this before you do your actual lab report, in addition to looking at those sample labs I showed you. But if you scroll down partway, here on this page, page 2, is a formula for percent difference, which says largest minus smallest divided by the average. If I take my two answers that I got, 0.79 versus 0.777, I can subtract them from each other and divide by the average, and that will be my percent difference. So after a little bit of work in Excel or Sheets, it looks like 1.66% difference or so. That's pretty darn good, all right? If you've got 5% difference, you should feel like you nailed it, all right? You definitely have good answers, right? Good results. Wonderful. So that is this first table filled out all the way for constant velocity. Your next one, these numbers mean nothing, but next thing you do is positive acceleration, right? Those graphs, and you would do it virtually the same, right? This and this really aren't all that different. The graphs look slightly different. I mean, okay, the graphs look different, but it would be the same process, right? If you wanted to find the area of, let's see, this rectangle and triangle, you could do it, and it would be the same thing, right? Not really any difference. And then, of course, using the position graph, you'd subtract the two values to get the displacement. Now, the only one that's really genuinely different is negative acceleration. So I'm going to clear these values out and then show you how do you get the values for negative acceleration, because that's a little bit more work. All right, negative acceleration then. You'll notice there's a lot more like things, right? X naught, X max, what do all those refer to? Well, those are referring to different moments in this position versus time graph. X naught would be here. X max, you could probably guess, would be at the very top. And X final would be here at the end. All right, just like with other things, I can look at my data table to determine what each of those are. So looks like my initial position is 0.2. Okay, so I can write down then, or not that one, I can write down 0.2 for X naught. Then, here we go, I can look through here until I find sort of the largest number for the position. And looks like, what's going up? Looks like 0.62 is X max, because that's as high as it goes. All right, that means that delta X up is going to be 0.42. In case you don't see it, that's the difference between these two values. Right, 0.2 and 0.62, it must have gone up 0.42 from the bottom. All right, X final would be, we'll scroll down, and there, 0.34 is its final position. Sounds pretty easy to pick out. Delta X down would be the difference between X final and X max in that order. Remember, it's whenever you're trying to find a delta, it's always the later one minus the earlier one. So we'll say the final minus initial, but 0.34 minus the 0.62. So that's going to be negative 0.24, I believe. All right, you can correct my math later if I've subtracted wrong. All right, and then delta X total would be just the difference between X final and, no, that's definitely not right, 0.28. X total would be the difference between X final and X initial. So 0.34 minus 0.2, that's 0.14. Now, if that was too fast for you, you can pause, take a moment, see if you can figure out how the numbers there are related to each other, or pause and scoot back a couple of seconds, have me explain it to you again. But these numbers are more or less pick off the graph and subtract the correct pairs of numbers. For my velocity versus time graph now, equation of line, all right, whatever, you have that on the graph. Acceleration, that's the slope of the equation, which apparently is not on the graph because I forgot to add it. Okay, fine. But you know how to get those. All right, delta X up and delta X down, and then delta X total, right? There are three of them, just like over here. And the way that you calculate the things is going to look slightly different on this negative acceleration graph because there's not really a rectangle here, right? It's all triangles. Okay, so to that extent, it shouldn't be any more challenging. You know how to find the area of a triangle, but careful with where you think the triangles are, okay? The area that you find is always relative to the x-axis. So here's your triangle, right? So that area is what we're finding. This requires me to, look pretty carefully here in my my velocity versus time values to figure out where things are. Oops, I went over. So for my first data point here, I can look up the initial value for the velocity is 0.58. It's of course 0 right there. So that means that the height of that triangle is 0.58. Okay, no real subtraction required. For the time though, be careful. That will involve subtraction. The initial time is 0.8. And now to figure out when this moment happens, I'm going to have to look at my data table. And yeah, technically there isn't an exact moment when the velocity is exactly 0 according to these data points. So I could take these two and like make the average of them. That seems like more work than is necessary. I'm just going to declare it, how about 2.2? All right, maybe it's technically 2.225, the average of 2.2 and 2.25. Whatever, it's 2.2. Good enough for what I'm doing right here. And looks like then that means that the base is going to be, well, also 1.4 seconds. Whew, amazing coincidence there. Okay, then 1/2 base times height. There's my area. I'll plug in everything I've got. Base, height, and calculate the area. And Excel, gosh darn it, Sheets informs me that the area is 0.406. Okay, now I wonder, how does that compare to my position versus time graph? 0.42, that's pretty good, right? It looks to me like that's pretty similar. All right, now from there you would do the same thing to get delta x down, except you'd be using slightly different data points, right? But same idea. The only quirk here is, remember, this area is negative area. Area below the x-axis is negative area. All right, now that's going to be hopefully something relatively similar to negative 0.28, but the process is exactly the same as what I did here, right? Look up two data points to get the, the time interval. Look up this final velocity to get the height of your triangle, 1/2 base times height. You get numbers. You hope that they are similar to negative 0.28. I'm going to just pretend it was negative 0.27. Awesome. I'm so good at physics, at least making up numbers. So then that means that my delta x total would be, well, let's see, we'll add these two together, really subtract, and that's 0.136. Which is very similar to 0.14. Okay, that's it. That's really what you got to do. Now, finally, we would calculate percent differences. Fair warning, this one here might be huge. Why is that? For delta x total, if your total displacement was, let's say, 0, the way the formula works, you could get actually infinity percent or like 200%. Which is clearly upsetting. So if you get a large percent error for delta x total, do not be concerned. That's actually pretty normal. For delta x up and down, those should be ideally pretty small, small numbers. Okay, that's it. Let me know if you've got any questions. Talk to me outside of class or in class as appropriate, and I'll get you headed in the right direction if you need some more help with this. Hope that helps. Thanks, guys.